Hi everyone, welcome to the recitation 2 of our course. And in this recitation, I'd like to talk about the different numerical systems and the convergence between these numerical systems. In this recitation, we would like to talk about 3 different numerical systems, including the binary, the decimal, and hexadecimal numerical systems. Okay, so before the recitation, let's just give a brief introduction to the purpose of using different numerical systems. And as far as we all know, in our daily life and in the normal mathematics, we may use the decimal numerical systems, which means that our base is 10. And when we count the number from 1 to 11, it is like this. So it is from 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we come to 10, and we need to add 1 to the 10th digit of the decimal number, and it goes to 10. It is 10. But in binary numerical systems, the things are totally different. For the binary numerical system, the base is only 2. Which means that for each digit of a binary number, the value in this digit can only be 0 or 1. Because the base is only 2, so there are only 2 values in one digit. But for the decimal numerical systems, for decimal number, because the base is 10, so we have 1 to 9. In total is 10 values in one digit. Okay, so this is the corresponding table between binary number, decimal number, and hexadecimal number. We will use this table later. So the purpose of using the binary numerical system is because that we all know the computers, the digital devices are comprised of some semiconductors, and there are only 2 states of these semiconductor devices, the opening state and the closing state. Therefore, we have to use the binary number to do the computation. So this is the usage of binary number, and in order to express the binary number very conveniently, so we introduced the hexadecimal numerical systems and the hexadecimal number. Okay, so now I will talk about the corresponding relation between binary number, decimal number, and hexadecimal number. So because a binary number has a base of 2, so 0 is corresponding to, so 0 in the binary number is corresponding to 0 in decimal and also 0 to hexadecimal. And if binary number is 1, so it's also the same. But when we come to the third line, different from decimal number, so because only 2 values within one digit of a binary number, so we have to add 1 to the second digit of a binary number. So the binary number will go to 10, and it is corresponding to a decimal number of 2 and also hexadecimal number of 2. Okay, so we add 1 to the last digit of a binary number, so it goes to 11. The 11 is only corresponding to 3. Okay, so if we go to 9, so 9 is 1001, and it is corresponding to 9 and also 9 in hexadecimal. So now, since it's different when we go into 10, so for a decimal number, we have counted to 9, and when we counted the number into 10, we will add 1 to the 10th digit, right? So it will become 10. But for the hexadecimal number, because the difference between the 3 numerical systems is only the base. So the hexadecimal uses a base of 16, but in our Arabic repetitions. So we only have 10 numbers, right? We only have 0 to 9. So if we want to express the 11 in one digit, we have used the A. So the 12 is corresponding to B, and the C is corresponding to 13, and also F corresponding to 15. So for a hexadecimal number, in one digit, there are 16 values to choose. So in one digit of a hexadecimal number, the value in one digit can be from 0 to F, which means 15. Okay, so in total is 16 values. So now when we comes to 10 to 15, the hexadecimal will still be one digit, and it is corresponding to A to F. And also for binary, it is from 1010 to 4 ones. Okay, so it is just the corresponding relations. Okay, so now I think we need to just talk about the conversions between binary number to a hexadecimal number. I think this part is the most easiest conversions between two numerical systems. Why we think that the conversions between binary numbers and hexadecimal numbers are the simplest conversions? Because there is a stable corresponding relation between binary numbers and hexadecimal numbers. You can see. So 4 digits in a binary number will be corresponding to 1 digit in a hexadecimal number. So such a corresponding relation is stable in all hexadecimal numbers and binary numbers. Okay, so now if we want to just convert the binary number, the 8-digit binary number 01011010 to a hexadecimal number, this method is just to divide the 8 digits into 2 groups. So each group will have 4 digits. The first part is 1010, and the second group is the first group is 0101, and second group is 1010. And we use the reference table. We can see the 0101 is corresponding to 5 in hexadecimal number, and the second group 1010 is equivalent to A. If we look at the table, right, 1010 is corresponding to A. So the hexadecimal value will be 5A, right? It is pretty simple. So sometimes if the number of digits of a binary number is not the times of 4, or for example, the binary number has only 7 digits or it has only 5 digits. So how to convert such a binary number to hexadecimal? It is pretty simple. For example, a number is 11000. We wanted to convert to hexadecimal. So we just add 30 to such a binary number, and the number of digits of the binary number will come to 8, which is the times of 4. Okay, so we also split it into 2 groups, which is 0001 and 1000. And later we check the table. So 0001 is corresponding to 1, and 1000 is corresponding to 8. So this number will be corresponding to 18. So if we want to just represent the numerical systems of a number, we will in most cases we will use the full note. which is like sorry, it seems like there is no full note. Okay. So we will use a full note to represent the number and to just express the numerical systems of this number. So because 19 is a hexadecimal number, and we will use 16 as the full note of this number. Okay. So this is the special case when the number of digits of the binary number is not times of 4. So now we can just talk about the conversions from hexadecimal to binary. So we have talked before, the corresponding relation between hexadecimal to binary is 1 digit in hexadecimal number is corresponding to 4 digit in the binary number. So B, when we check the table, B is equal to 1011, and 8 is equivalent to 1000 right here. So it's clear that hexadecimal number B8 is corresponding to 1011, 1000. Okay? So the conversion from hexadecimal to binary is pretty simple. So now we have talked about the first pair of conversions between binary numbers and hexadecimal numbers. Okay, now let's talk about the conversions between a decimal number and a binary number. So first we can talk about the representation method of a decimal number. So the decimal number is 9,732,112. So it is a decimal number with 7 digits. Okay, so we have already know the base of a decimal number is 10, right? So the first digit of a decimal number is the base of 10 to the 0. 10 to the 0 is 1, right? So the second digit will be the base. The power of the base will be 1. So the second base is 10 to the 1. And the third digit, the base is 10, is also 10. But the power is 3. So for the third digit, the power is 2. So for the third digit of a decimal number, it will be 10 to the 2. And next is 10 to the 3, 10 to the 4, and 10 to the 5, and 10 to the 6. So when we want to represent our number of 9,732,110, it will be like, so it will be the value in the first digit is 2 times the base of the first digit, which is 2 to the 0, plus 1 times 2 to the 1. And the next digit will be, the value is also 1. So it is 1 times 2 to the 2. And the value in the first digit is 2. So the base is 10 to the 3. So it will be 2 times 10 to the 3. And the next digit, the value is 3. Here, the value is 3, but the base is 10 to the 4. So it is 3 times 10 to the 4. And times 7, plus 7 times 10 to the 5. And now 9 times 10 to the 6. So it will be 2 plus 10 plus 100 plus 2,000 plus 30,000 plus 700,000 plus 9 million. So each digit times the value in each digit times the base of each digit, and we add them together, and we have got the final representation for a decimal number. So this is how we organize a decimal number. So now, let's imagine if for the binary number, we have talked before, the difference between decimal number and binary number is just the difference between the base. So the base of a binary number will be 2, right? So the method for organizing a binary number is also the same. It is also the value in this digit times the base of this digit, and we add all the values in each digit together, and we will get the final number. Okay, so now let's look at the process for converting the binary number 10101001 into a decimal number. So the base for the first digit in the binary number will be 2 to the 0, and next digit is 2 to the 1, and 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5. So please tell me, if we use 1 times 2 to the 0, what is the value in the first digit of a binary number? So 1 times 2 to the 0, it is 1 times 1, so it will be 1. The value in the second digit of a binary number is 2, and the base is 2 to the 1, which is also 2. So 0 times 2 is 0, and the third digit, the value is 1. The base is 2 to the 2, which is 3. So 2 to the 2 is 4. So 1 times 4, the value in this digit is 4. And next is 0, and next is 1 times 2 to the 4, it is 1 times 2 to the 1 times 16, it is also 16. And the last digit is, the value is 1, the base is 2 to the 2 to the 6, and it will be 1 times 2 to the 6. The value in this digit is 64. So we add up all the values together. It will be 64 plus 0 plus 16 plus 0 plus 4 plus 0 plus 1. So the final number will be 85. So this is the convergence from a binary number to a decimal number. Okay, now when we just review this corresponding table, we can use another method to get the corresponding relation between a binary number to a hexadecimal number. So if we look at the binary number 1000, so let's imagine the first digit, the base is 2 to the 0, and 2 to the 1, 2 to the 2, 2 to the 3. So what is 2 to the 3? 2 to the 3 is 8. So 1 times 8. Therefore, it is corresponding to a decimal number of 8. Okay? So for binary number 1001, so the base of the first digit is 2 to the 0, so it is 1. So 1 times 1 is 1. And the last digit, the base is 2 to the 3, so 1 times 2 to the 3 is 8. So 8 times 1 is 9 in decimal representation. Therefore, later you don't need to remember the corresponding relation between the digit in binary decimal and hexadecimal numerical systems. You don't need to remember the reference sheet, the reference table. You can just make a very simple computation, and you can get the corresponding relation. Okay. So now we want to talk about the update process for converting a decimal to a binary. So let's imagine when we do the conversion from a binary to a decimal, we just we just multiply the value in each digit by its reading base, and we add all the values together, we get the decimal representation, the decimal values for a binary number. So when we want to convert a decimal number to a binary number, the opposite process it is just to divide the decimal number by 2, repeating this operation multiple times until reaching a result that cannot be divided by 2 any further. So the process is like this. So we use the decimal number 72. We divided 72 by 2. So the result is 36 and the remainder is 0. And 36 over 2, the result is 18. Remainder is also 0. So 18 by 2, it is 9. Remainder 0. 9 by 2, the result is 4. Remainder is 1. 4 divide 4 by 2, the result is 2. Remainder is 0. Divided 2 by 2, the value is 1. The remainder is 0. And you need to remember that you need to be very careful about the last line. So if we divide 1 by 2, the value is 0, and remainder is 1. So I know some of you may be confused about this, but it's very easy to just revise this process. So because we can use the result 0 times 2 plus the remainder 1, so it is equal to 1, right? If we look at the opposite process of the last line, so 1 divide 1 by 2, because 1 is smaller than 2, so the result will be 0, and the remainder is the number itself, so it will be remainder will be 1. Okay, so now we just need to write the result from the last line to the first line. You need to remember this order very carefully. You need to write the number from the last line, the remainder of the last line to the first line, which is 1 0 0 1 0 0 0. So this number will equal to 72 in the decimal representation. So if we look at the remainder of each line, so if we write in the opposite order of all the remainders, it is from 1 to 0. It is 1 0 0 1 0 0 0. And this number will equal to 72. We can do a very quick verification. So we all know the first digit, the base is 2 to the 0, and 2 to the 1, 2 to the 3, 2 to the 4. So it is 1 times 2 to the 4, it is 16, right? And next is 2 to the 5, 2 to the 6, 2 to the 7, and 1 times 2 to the 7. Yeah, 2 to the 7 is... Oh, I'm sorry. So it will be 2 to the 0, 1, 2, 3. Oh, sorry. It is 1 times 2 to the 3. It is 8. And 2 to the 5, 4, 5, 6. 2 to the 6. It is 6. 2 to the 6. It is... Yeah, so 2 to the 6, it is 64, and it will be 72. You can do the verification by yourself, because the base of the first digit is 2 to the 3, and the 7th digit, the base is 2 to the 6, and 2 to the 3 is 8, and 2 to the 6 is 64. So we add 8 to 64, the result is 72. So it demonstrates that the converting between a decimal number 72 to a binary number 1001000. It is correct. Okay. So in order to train your ability for converting a decimal number to binary number, we can just play a game. So this is the address, the web address for this binary conversion game. I can open it up and tell you how to play this game. Okay, we can choose the classical mode. It is just the instructions, and we can click OK. Okay, so the first number is 1. So if we want to represent 1 into 3 digits in a binary number, it will be 001, right? So we just select the 3 binary digits, which is equal to 1 in a decimal number. Yeah, it is correct. We have done this task. And 5, let's imagine 5. 5 is equal to 4 times 1. So it will be 2 to the 2 times 2 to the 0. So it will be 101. It is 5, right? And 2 is 2 to the 1. So it will be 010, right? And 7. So 7 will be 4 times 2 times 1. So it will be 2 to the 2 times 2 to the 1 times 2 to the 0. So it will be 111. And 0, of course, it is 000. Okay, we have done the test for the level 1. Okay, so level 2, it is a convergence between the decimal number and our 4-digit binary number. So 4, it is, of course, 0010. I'm sorry, 0100. So it is like this. Yeah, it is 4. And 7 is 0111 because it is 4 times 2 times 1. And 9, it is 8 times 1. So it will be 1001. 1001. Okay, we have done. So 15 will be 8 times 4 times 2 times 1. So we need to select 4, 1. So it will be this. Now 3, it is 2 times 1. So it will be 0011. Okay, we have done the task force on level 2. And you can just play the game by yourself. Now we have already covered the contents of the convergence between a hexadecimal number and a binary number, and also the convergence between a decimal number and a binary number. So we can come to the last part. It is a convergence between hexadecimal number and decimal number. So we have talked about before the difference between a hexadecimal number and a decimal number is the difference between the base. The hexadecimal number uses a base of 16. And also the power of the first digit is also 0 and 1 in the second digit and 2 in the third digit. So the base for the first digit is 16 to the 0, which is 1, and 16 to the 1, which is also 16. And for the third digit, 16 to the 2, it is 256. So we also need to just multiply the value in each digit by its base. And we add up the values, the results in each digit together, we can get the decimal representation. Okay, so it is 9 times 16 to the 0, which is 1, so it will be 9. 8, we have talked about before, 8 is equal to 10. So it is 10 times 16 to the 1, so it will be 116. And 2 times 16 to the 2, which is 256. So the values in this digit will be 512. So we add up 512 plus 160 plus 9. So the result will be 681. So this is the conversion from a hexadecimal number to a decimal number. Okay, so the last part is also the same. If we want to just convert a large decimal number 680 to a hexadecimal number, so how to do this? The process is also the same as the conversions from a decimal number to a binary number, but the number for division is different because the base is 16 now. So we need to use the decimal number 680. We divide 680 by 16. So the result is 42 and remainder is 8. We divide 42 by 16. The result is 2 and the remainder is 10. And we also know the 10 is corresponding to A in a decimal number in one digit. So 2 times divide 2 by 16. The value is 0, the result is 0, and remainder is 2. Because 2 is smaller than 16, so it's clear that the results can only be 0, and the remainder is the number 2 itself. So we also write the remainders from the last line to the first line in an opposite order, which is 2a and 8. So decimal number 680 to a hexadecimal number, the result is 288. And also we can do a quick verification. We can just convert the 288 to a decimal number. So it is 2. So it is 2 times, it is 16 to the 2, right? So it will be 256. And the second digit is A. The base is 16 to the 1, which is 16. And times 8 times 16 to the 0, which is 1. And the result should be 512 plus 160 and plus 8. So the result will be 680. Yeah, so it demonstrates that our conversions from the decimal number 680 to the hexadecimal number 288 is correct. Okay, so that's all for our course. And one last thing, we can just talk about the colors and hexadecimal notations. And you can also open up this webpage, and we can talk about the hexadecimal notations for a color value. I think you should know that each value of a color is composed of 3 base colors, which are red, green, and blue. So the value for each channel, because one color has 3 channels, red, green, blue, and the value in each channel, we add them together, we will get the RGB representation for a color. So if we want to know the RGB value for the dark, actually the dark is R as 0 and G as 0 and also blue as 0. So the representation, the binary representation for the value black will be 6 zeros. And in the opposite direction, the color red will be 255 and also 255 and also 255 for 3 channels red, green, blue. And if you do a conversion from a decimal number 255 to a binary number, it will be FF in the hexadecimal number. Okay. So if the red channel is 255 and the value is FF and T is also FF and B is also FF. So 6F in the hexadecimal notation, it represents for the color of white. So for the red, something different. It is E2, 2C, and 2C. Sorry. So 2C is equal to 60 in the decimal number. So now we know 6 digits of a hexadecimal number will represent for a value of a color. So if we look at the orange, so the hexa representation is FF8000. So the red channel represents for the first 2 hexadecimal digits of the color, which is FF. And the green channel represents for the intermediate 2 digits of a hexadecimal notation, which is A0. And A0 in hexadecimal representation is corresponding to 128. And the blue channel is 0, and the hexadecimal digits, the 2 digits are 00. Okay, so this is the hexadecimal notations for a color. Okay, that's all for our recitation 2. You need to do a lot of practice to make your conversions very fluent. And if you don't understand anything, please come to my office hour. And don't forget to just submit the attendance worksheet, which I have already posted in the pages of Canvas. Okay, bye.